Hello everyone, my name is Liam Bennett and I'm currently a master's student at the University of Alberta. I'm doing my master's under Dr. Jeff Bovair in mining engineering in the Civil and Environmental Engineering Department. Today I'm here to talk about one of our current projects where we extract tree characteristics from RGB aerial imagery and how these characteristics can be applied in a wildland fire setting. The province of Alberta experiences wildland fires every year. If you live in Edmonton, you may have heard about the fire in Parkland County earlier in May. Normally, wildfires are considered part of a healthy and natural forest cycle. However, they start becoming a hazard when they encroach on people, property, and industrial assets. There are a number of decisions that must be made before and during a wildfire event, and these decisions can be driven by data about nearby fuels. So where is there room for automation? Wildfire behavior is typically influenced by the wildfire triangle, that is weather, local topography, and fuel. Weather is simple enough to get, and topography doesn't change year to year. Fuel is the last corner of the triangle and is harder. We have less samples and they must be manually categorized into fuel maps. Fuel maps show dominant fuel types within grid cells, as you can see to the right. This data is collected via on-site surveys and satellite imagery and is fed to empirical models which forecast the fire's movements. To the right we see such a model predicting the spread of the fire to the west of Edmonton that we mentioned earlier. We are proposing a new method to gather this data. We conduct surveys using a UAV, in our case a Mavic Mini. So create a flight plan for the area and collect high-resolution RGB imagery. This allows for large swaths of forest to be collected in a time-efficient and cost-effective manner. Anyone can fly one of these drones. They're consumer grade. This is a deliberate choice we made to reach municipalities that might not have room for aerial photography or LiDAR in the budget. This is much more accessible. Next, our surveys are stitched and orthorectified, and manual annotations of each tree were applied, so boxing each tree. These annotations, and there are about 5,000 trees, were then used to train a neural network to identify and classify trees. The classification of trees as coniferous or deciduous is an important property in fire spread models. Coniferous trees are of higher concern as they can dictate fire behavior. The accuracy of the models was then assessed by k-folding through the survey set, so excluding one survey from training and testing on it. Currently we see about 83% recall and 69% precision when drawing boxes around trees, and the tree is properly classified as coniferous or deciduous about 90% of the time. So now that we can identify and classify trees, we can begin deriving tree stand properties and fuel attributes. Of particular interest here are tree density, tree type, and tree size, which is two parameters, crown width and tree height. Tree type can be determined by the model we previously discussed, so coniferous or deciduous. Tree density can be determined using the number of boxes identified in a certain area, and you can see a heat map of density here to the right. We can also estimate tree size, so crown width from the box sizes which are fit to the tree by the neural network, and estimates of height can be made using the point clouds generated when we stitch the image. Again, this is performed using only a consumer grade UAV and included RGB camera. No additional sensors like LiDAR are required here. One application of this data is FireSmart home assessments. FireSmart is a Canadian wildfire preparedness initiative that outlines home assessment procedures that can be used to assess properties. Some of their inputs include proximity, density, and type of trees near the structure they are examining, data that is usually collected by on-site visits of forestry or wildland fire experts. The results from this work could be leveraged to inform these assessments as well as mitigation techniques like tree thinning or other fuel removal that can downgrade the hazard a fire would pose to an individual structure. On a community scale now, areas of communities can be classified by their exposure to ignition. Generally speaking, proximity to coniferous fuels, including mixedwood areas, increases the exposure of an area. Coniferous fuels generate more embers or firebrands. This map shows a community assessment that was generated with a technician manually annotating aerial imagery and performing field visits to verify uncertain areas. Automating the process with the work shown today could lead to finer fuel maps that are more practical to generate, allowing for problem areas to be better targeted. This project continues to grow, and there is a rough roadmap for its anticipated direction. Collecting additional survey data is one task that would benefit the project, with the eventual goal of classifying trees on a species level rather than simply coniferous or deciduous. Next, completing a community assessment in Alberta would involve numerous surveys around the outskirts of this community, as discussed on the previous slide. Another goal is expanding to satellite imagery. This is something that we've begun to explore. A density map of trees identified by a separate neural network can be seen to the right. And finally, tailoring our workflow's outputs to serve as inputs to current FBP models could allow for more recent data to be used to predict fire spread. Well, this has been a brief summary of our project. Thank you for listening, and I hope it sparked some interest. Again, my name is Liam Bennett, and I will be available in the Zoom if you would like to discuss or if you have any questions. Thanks.